columns, I get 10, I would have 16 pairs over C. And there should be some nice pattern we could deduce about these numbers. Yeah, do we see
I
what
see one.
Yeah. Pardon?
Yeah.
Yeah, sure. Yeah, this is nice and simple. But lo and behold, even but you could see what it is. Oh, look, nice and simple. And now if you want to do higher moments, I'm going to do higher moments about the mean. So we have to manipulate the variable a little more. So you basically send the variable to this. So this is the answer. This is our expected value. Divide by our expected value. And then you choose the SBS operator. And you let S be equal to 1, and you look at the coefficients. Okay, so let's see what we get. Now this is where it gets kind of interesting. When the machine is truly helpful, I wouldn't want to do this by hand.
Real fast, sorry. The probability distribution on the colorings themselves is just uniform, all the colorings are equally likely?
Yes.
So it's like any square we just color randomly?
Yes, yes.
Okay,
Nothing's, no, there's nothing. I'm not that sophisticated about probability. No, yeah, it's all equally likely you grab it. Okay, so let's take a look at what we got. Let's look at some of our output. And the output we want to look at that gives the moments about the mean, let's ignore this, is this program. So this is moments. This is going to be our number, the row size. This is what moment we're working with. Okay, so I'm going to make it about the mean. So if I let it be first moment, you get this. Here's my second moment. Oh, look, isn't that very nice? Look at these nice patterns. We get the same numbers. Wow, guess what happens when you take the third moment? Now this is, of course, with them being 2. Same numbers. So we could hope, and we can notice the difference between this. Let's go back to the second. I was very excited about this. So when I saw it at first, I thought, oh, I'm good at finding patterns, even I. This is C minus 1. And this one we factor is, of course, yeah, so it's not. So what we hope the next case through, we'd get the same coefficient times C minus 1 times C minus 2. No. Unfortunately not.
Yeah.
Yeah, here's the reason when you start doing this combinatorially, the numerator, the denominator, you can't fix as the power. It gets really messy. So now our goal is to try to figure out a way to get the machine to calculate these in a different way to see the pattern while I'm putting in arbitrary m and n. So here I fixed m being 2, and then now in each case I'm fixing n.
Can I go up a little bit?
Sure.
So this is the fourth moment?
That's the fourth moment.
Yeah. Is the fourth moment about the mean?
Yes, these are all about the mean.
That's a bit fishy. It's not as simple as the normal?
I don't think so.
Okay.
I haven't worked, but it's not very nice.
It's fishy. I would expect to be as simple as normal. Then the limit, the fourth moment should be 3. So here it goes to 0, it looks like.
Maybe.
And C goes to, oh no, sorry. No, C goes to infinity. Yeah, I guess that not. And then C is, yeah, I guess not, okay.
Yeah, no, it's the program.
No, it doesn't have to be, I guess.
Yeah.
Depends on C, right?
Yeah, depends
These are
on
the
C.
exact values.
Mm-hmm.
Okay, but if C goes to infinity, that makes sense. Yeah, maybe not. Yeah, forget it.
Yeah, okay, that's okay.
Yeah, probably right.
Unfortunately, I know when I started to do these calculations
So you check
by
it?
hand, yeah, by 2, I can check, I've checked 1 is easy, 2, and I've even pounded out 3 by hand, and this is okay, the pattern goes through. The problem is when you get to 4, when you're doing the lower moments, the numerator is always going to be, not the numerator, the denominator, when you're doing this by hand, you're going to end up counting pairs is what's happening. The denominator always is nice when you do the second moment at C2, when you do the third moment, everything
sorry, take it back. Hey, what you should do is divide.
Yeah.
No, it's probably has to make the normal. When you divide by.
Yeah, but I was going to say, what happens, the reason it starts to fall apart is you would hope when you get the fourth moment, you could always have a C to the fourth at each time, but you can't. You could get C cubed, C fourths, and so it really does start to.
Yeah, take it back. No,
yeah, it's a mess. It becomes nasty. So now, but my goal is to try to take my combinatorial proofs I have for the first moment, the second about the mean, the third. And adjust it to get 4, because it's going to give me the fourth moment with it instead of having.
No, it would be nice to do the fourth moment divided by the square of the variance.
Okay.
And then look at the values.
Okay.
That should be.
Yeah, you're better at asymptotics than me.
It's a 10.
Yeah, but unfortunately, I mean, So that's why it starts to fall apart and the patterns doesn't really continue. So my goal is to now have other programs that are going to try to compute the combinatorial proofs, put them in the computer. In the combinatorial proofs, you'll have a C, you have an M, and you have an N. And we're going to see what patterns. The ultimate goal is to hopefully get some kind of formula for the fourth mean, the fifth mean in terms of M, N, and C. That's going to be really nice. Okay. All right, so and in fact, we could do this.
But for the variant, you have a nice formula?
Pardon?
For the variant, for second moment?
Yes. Mm-hmm.
So can you go, is it here?
Yeah, the formula for the second moment is about, which we could talk about how we can discuss it. The formula for the second moment about the mean is...
So you have generating function in T?
Yeah. Mm-hmm. You want to see the generating function. Yeah, but as I said, for the second moment about the mean... I'll do this up. I don't need this because I know. Which you can end up showing. And I'm going to tell you, just to remind you.
So it's still M is 2?
Yeah, so it's M and minus M minus M.
That's why the M and N.
Yeah. Mm-hmm. I'm just going to have to figure that. So it doesn't matter.
Okay.
Oh, second moment. I'm sorry, second moment. Oops. No, second moment, you just have C minus 1. Sorry. Third moment has the C minus 2. Yeah. We have C minus 1. Just have C minus 1, sorry. Then we have the next, we're just C minus 2 over Q. So, yes, that's...
Yeah, the biggest thing to take this.
Yeah, and so the goal is to take this, see if I could get these formulas and push it to 4 or 5, but I don't have these nice patterns. All right, so if I had more time, I'd show you what the pattern continues. So let's now talk a little bit about how to combinatorially do this with the computer. I don't have time to show you how to do it by hand. So what the computer has to do is let's talk about how to do the first moment quickly and then the second about the mean. Okay, so what I'm going to do is I'm going to tell x be the expected value. I'm going to work with try to compute e to the x. Where x is the number of edge adjacent pairs. The same color. And then, if I want to do the second moment, the key, if we were doing this combinatorially, it's easier for us humans to work with choosing pairs. So this is, we're going to basically, when we're doing e to the x, we're going to take our m by n grid, and we're going to say, how many ways we want to count the number of pairs in this thing. So how many ways can you make a single pair? What type of pairs are there? There are pairs that go horizontally, or there are pairs that go vertically. So how many ways can you make a pair that goes horizontally? How many ways can you place up a pair that goes horizontally in this grid? Well, you have n, yeah, and these. You lose the last row. And then you have to color it. You could give this pair any C color. And the rest of it, we have C to the M, the other squares I don't care about, and the colors and then I divide. You could do the same thing for the vertical pair, but you interchange the role of M and N, you add it together, and you get exactly what we were saying. You get 2 to the Mn minus M minus N over C. Okay? Now, when we want to get x squared, we got to work with 2 pairs. So how can we put 2 pairs in this thing? And you want to make sure we have 2 adjacent squares. Well, there's all kinds of ways you could do this. You could take your grid. You could have this. You could have L shapes. You could have 2 horizontals, 2 verticals. You could have blocks of 3, so they're not all the same shape. So we're going to call the things we're going to place in here animals. I'm going to start by building a set of all connected animals, and then we're going to count the number of pairs that are in this animal, and they have to be the number of pairs. I have to cover, when we make our pair thing, it has to be cover the whole animal.
You have to tell the people this is a physics terminology animals.
Okay.
That is called polynomials.
Polynomials?
Right.
Sorry, polynomials.
Polynomials.
Yeah, polynomials.
Polynomials, yeah, I see. Okay.
Polynomials.
But I think it's listed in Sloan as animals. Doesn't he list it?
Yeah, it's good. It's a
Yeah. Okay.
Animals.
Okay, so if you like polynomials, I will be referring to it as animals. As you'll see by the program, I will refer to them as, if you want to think in your mind polynomials, please do. But we're taking like little blocks of cubes of all kinds of shapes, and then we're going to see how many pairs, adjacent pairs are in each shape. And so when we do this, if we're doing square, we got to make sure we're going to throw enough of these little shapes in, so that we have altogether 2 separate pairs, don't intersect. If we would do 3, we'd have to throw enough of these little shapes in that you'd have 3 pairs. So for this case, I want to do 2 pairs. So here's how we go about doing this. We go to the next Maple program. We inductively build our animals by attaching a square at the end. This is an excellent exercise in recursive programming. And now when I do this, I'm always going to make sure when counting, the trick is to make sure your animal has a preferred square, and that bottom lower left corner, or your polynomial square, there's going to be 0, 0. And when I'm talking about the animal, I'm going to make sure, but the point in the animal, I think it's in the center of the animal. I think it's a little square around the center of the lattice point. Okay, so here we build our animals. And then we have to be fancier with our animals. We have to build what I call a path animal. Okay, so here's our set of animals. So we have 2 squares, and I'll explain what this means. Here we have animals or polynomials with 3 squares, with 4 squares, and lo and behold, the machine does it for you. And this is the sequence of Sloan. So once you got it up to 10, we knew it slows down a little bit at 10, but it does it. So now I have to take a typical animal, and I have to cover it with pairs. And that is done with the program. I'll show you an example of how to read an animal in this machine. And that is done with the program PBAN, this program. So let's take a typical animal sample of what we're working with. So for example, how would the machine record this animal or this polynomial? So the machine would record this as an ordered pair. First piece of it is going to be A, the animal piece, where you're going to get a collection of square centers. And the second piece is going to be A. And the second piece is going to be edges, where you have sets of ordered pairs. And so therefore the machine would say, okay, I have the edge 0, 1, the edge from 0, 0 to 0, 1. I have the edge from 0, 1 to 1, 1. And I have the edge from 1, 1 to 0, 0. So there is more information. This picture, there's 6 ways you can make what I call path-connected animals. You just have to rule out a few. The key is that every path structure you make, every edge structure you make has to cover the whole animal. Has to be a neighborhood of 0, 0. Because I don't want to have something that looks like this in our picture, because I don't want this, because that will be picked up by adjoining two of these single animals. So I want everything to be connected. So once you get that, you basically then have to take the number partitions. So then you have to say, I want to get k pairs. In this case, I want to get 2 pairs. And then I have to take the numeric partition. How many ways can I make the numeric partition 2? Well, I can make the numeric partition 2 as 2, or 1 plus 1. And so you have to then have a program that takes all your numbers, splits them into the numeric partitions, and then takes all these path-connected animals and forms the ways you can do it. The set says it's a path-connected animal, so that the total thing could have 2. So for example, if I want to have 2 pairs, T2 is my set that there's 10 ways to do this. We could check. If you have, there's 10 ways you could take an n by n grid, and you could throw in a bunch of animals, and the animals could either be single pairs, or they could be one whole block which has 2 pairs, and there's 10 ways to do this. Okay. So now what you got to do, this is going to be a little rushed, is we got to take these pairs and we got to place them into the grid. So let me explain. Let me just do x squared at the end, and then I'll show you the end result. Okay. So what we want to do is I'm just going to choose 2 pairs. So basically, the trick is if you were looking at I would look at 2 pairs. I want to put in 2 pairs. There's 2 ways you could do it. You could put in an animal that has the form. Let's do it this way. I'll just draw the picture. It's easier. I can either put in animals of the form where they're 2 separate pieces, each one a single pair. Or you could put in 1 piece. So you could put in 2 pairs. You could put in 2 pieces, 2 pieces, 2 pairs. Each one gives you a pair. Or you could put in. This goes with the partition piece, 1 plus 1. Or you could put in 1 pair, 1 piece. Get a bunch of L's. Or you could get 3 blocks adjacent. You can put this in. So what you have to do is when you have an n by n grid, you can numerically tell the thing. If you have a single piece, you can numerically tell the machine the place you numerically fix M and M. No, is that my phone? Let it go. It never rings. Never rings until I won't want it to.
I know. Silence the cell phones.
I know, it never rings.
Yeah, speak up.
I know, it's horrible. I'm just ignoring it when they'll shut up.
No, turn off.
Get it.
Yeah.
All right. I'll turn it off. Yes, I'll turn it off. But
Oh, that ball that wasn't put on board.
all right, I'll turn it off. Sorry.
Okay. No, there was also about to speak us.
Yes, I know it's really bad. I'm sorry. Okay, so now that we had that faux pas, I just want to say, if you have a single piece, you can numerically fix M and M, and you can count the number of ways to put this in the grid, put the piece in the grid. And then you can have it solve for a placement polynomial. So once you have enough numeric data, you can then solve for a placement polynomial. Of the form A, M, N plus B, N plus C, M plus D is going to equal the number of ways to put in.
1 minute.
Yeah, 1 more minute, the animal. Okay, so you solve for this, and then you basically, that's your placement polynomial. You take the placement polynomial, You count the number of, you then multiply it, if you have a single piece, by c, and then you multiply it by c to the mn minus the number of squares in each of these animals, divided by cmn. For 2, you have to adjust your placement polynomial. It becomes a 9-degree placement procedure, numeric placement procedure. You get a 9-degree polynomial, in mn squared, n squared, m squared, n, so forth and so on. And you do the same idea. You place that in, you multiply by stuff out, and you get what you really need to get, which you end up getting. All right, let's rip all the way down to the bottom. It's a single one. Here we do it. You do it in 2 sets. The 1 set, the 2 set. So here's our placement polynomial for 2, and we can see that the shape of the polynomial we're placing is, in fact, this is what you solve for that. You end up multiplying this together, and you add the 2 pieces, and you end up getting what you want for your ex squared over 2, and then you can back solve for ex around the mean.
Thank you very much.
Okay.
Don't let me get to answer questions in private.
Okay.
Like to join us for dinner.